Hello, thank you for being here virtually today with us, and thank you to the organizers for having us. Today I'm really excited to tell you about Backbone and our package for extracting the backbone of bipartite projections. This is joint work with myself, Rachel Domagulski, Dr. Zachary Neal, and Dr. Bruce Sagan, and we are all from Michigan State University. We're very excited that Backbone is now published software in PLOS ONE, which the link you can find here. And for all things Backbone, including papers, talks, and any extra information you might need, Zach has a lovely page up on his website. So to start us off, what is a backbone? Well, the backbone of a bipartite projection is an unweighted or signed network that keeps only the most important edges of that projection. And the Backbone R package provides different methods for extracting this backbone. It's really easy to install onto your computer. You can just use install.packages and it'll load it right in from CRAN. So why would you want to use this package? Well, let's say that we use a co-sponsorship network to measure political collaboration between senators. So we want to know who works well together and who does not. Instead of asking these senators directly, maybe we keep track of which bills they sponsor, and we create this bipartite network where they've sponsored a bill or have not. When we project this network, we end up with a network where each edge weight corresponds to the number of co-sponsored bills between two people. And this edge weight is going to depend on how many bills each person sponsored and about how many people sponsored each of those bills. If we look at this visually, we might end up with something that's like a huge, dense hairball graph. So for instance, this is a visual representation of the 114th session of the US Senate, where we kept an edge between two senators if they had sponsored at least one bill together. In contrast, check out what happens when we use the Backbone package. Here's that exact same network, but now we've used Backbone's SDSM model and found only what we're going to consider the most important edges. We can now see that we have sort of these two different party systems going on, like we expect. Most edges occur between Democrats or between Republicans. So how does this work? Well, what Backbone's doing is it's using statistical tests to compare an edge's observed weight in our bipartite projection to the distribution of weights that it might expect under some null model. So particularly what we do is we consider an edge weight statistically significant if it's in the upper or lower tail of the distribution. So think back to if you're considering like a normal looking graph, if the observed weight you got in your projection was way up here in the upper tail, then we're going to consider that a positive edge in the backbone. For instance, two senators sponsored way more bills than we would expect them to at random. And the opposite for the lower tail. If that value was significantly less than we'd expect, then we're going to consider it a negative edge in our backbone. So the backbone package contains three different types of null models where we're comparing that observed edge weight to a distribution. Specifically, it contains the hypergeometric model. This lets the row sums exactly match the row sums in our observed bipartite graph, but we're going to allow the column sums to vary. The stochastic degree sequence model. Here, the row sums and column sums are allowed to vary, but match on average. And the fixed degree sequence model, FDSM. Here, the row sums and column sums exactly match the observed bipartite. So if you want to use one of these models with your data, what you're going to do is first get your data into R. This can be an adjacency matrix, a sparse matrix object, an iGraph object, a network object, or an edge list. And you're going to pick which model you want to use. So you want to think about which of the marginals you want to constrain and make your choice based on that. After you pick that model, what you're going to do is you're going to get back this backbone object. So say you use hypergeometric on your data, you get back a backbone object and it contains two things, positive and negative. These are both going to be matrices containing the probability of an edge under the null distribution having a weight equal to or above the weight observed in your projection, or equal to or below the weight observed in your projection. Now that you have that object, you can send it into the function backbone.extract. And here you can choose a significance level to which you'll extract your actual network. So you start with these matrices of probabilities, you send it into backbone.extract and get back the actual network. The backbone.extract function is really versatile. It gives you a lot of different options. The first thing you do is plug in your backbone object that you got from either hypergeometric, SDSM, or FDSM. You can then choose if you want to get back a signed or positive network. You can pick the significance test value, and this will always be a two-tailed test. You can choose whether you want to apply family-wise error rate test correction. And our options here are Bonferroni test correction and home Bonferroni test correction. You can also change the class of the object that you'll get back. So maybe you started with your data in the form of a matrix, but then once you extract the backbone and you have this network, you would rather deal with it as an iGraph object. You can do that simply by just setting class equal to iGraph. And we also have this narrative parameter. This will output suggested manuscript text and citations. And I'll show you what that looks like in just a second. So let's check out what each of these three different models that Backbone contains do. So let's consider again our Senate co-sponsorship example. So what we're going to do under the hypergeometric distribution is compare our values that we see to a distribution of bipartite graphs where the number of bills that each senator sponsored is fixed, but each bill can be sponsored by a varying number of senators. And if we want to apply the hypergeometric to our data in R, first thing we're going to do is call the function hyperg, and we're going to get out this backbone object. Here it's called hyperg_probs. And this contains those probabilities in the matrices positive and negative. Then we're going to take that object and plug it into backbone.extract. Here we can set an alpha value. Here I've set it to 0.01, and this will extract our network. I've graphed it here. This is all of the positive edges under the hypergeometric distribution of the 114th session. And we can see it is less of a hairball that we saw before. We're starting to see that two-party structure, but we can probably do a little better. So what about the stochastic degree sequence model? Here we're going to compare our observed data to the distribution where each senator sponsors about the same number of bills and each bill is sponsored about by the same number of people. Again, we call it just like we did with hypergeometric. We apply SDSM to our data, and then we plug those values into backbone.extract. And what this function is doing is it first is computing a probability for each cell in the bipartite matrix to be equal to 1, and then it's applying a Poisson binomial distribution to the weighted projection, as opposed to the hypergeometric distribution that we saw before. When this narrative equals true parameter is used, it will give back suggested manuscript text and citations. And this will print out information about your network that you're looking at, the citations for both the backbone package and the models that you were using, and a couple sentences about what it actually means to do this. And here again we can see what the network looks like under the stochastic degree sequence model. We can see that most edges are within party and there are very few bipartisan edges between parties. And finally, the backbone package has the fixed degree sequence model. Here we'd be comparing our observed values to the distribution where each senator sponsors exactly the same number of bills that they did in our collected data, and each bill is sponsored by exactly the same number of people. We don't have an exact distribution for this, so what we do instead is we sample from it using the curveball algorithm to create a large number of bipartite graphs to which to compare to. And you can choose how many of those bipartite graphs you want to generate using this trials parameter. So the larger the number of trials you run, the more accurate this distribution will be. FDSM also has this really cool parameter called dyad, which gives us the distribution for a chosen dyad. So for instance, if we want to look at the distribution between Senators Booker and Warren, we can add their names in here to this parameter. We can use either the name of their node or just the number of that node in our data. And since trials equals 1,000, what it's going to do is give us back all 1,000 values for the possible number of co-sponsorships they could have had. So we can plot this data, which we've done so on the left here, and then we can compare it to the actual value we observed. So in the 114th session, they had co-sponsored 98 bills. We can tell that this is definitely in the right upper tail of our distribution. And so in our network, after we use backbone.extract, we expect to see a positive edge between Senators Booker and Warren. So hopefully all of this is exciting enough to encourage you to check out the Backbone package. But if not, we also have some updates coming soon. Early February 2021, so right around the corner, we're going to introduce Backbone 1.3.0. This contains some functions that will help with easier model selection and give you some guidance on how to choose. It also contains faster SCSM computations, so that function itself will be sped up. And of course, we've thrown in a couple bells and whistles. And then this summer 2021, we are planning to release Backbone 2.0, which will contain models for general weighted graphs. So right now, Backbone contains these 3 models that all deal with bipartite projections. This new update will contain models for weighted graphs that do not necessarily come from bipartite projections. In addition to those software updates, we also have a manuscript coming out soon, which will aid in model selection. So SDSM uses different methods to compute probabilities to use the Poisson binomial distribution. Here we're going to talk about the accuracy of those probabilities that are generated. We also talk about the effects of different degree distributions in your data and significance levels. And we also compare the ability to recover group structure amongst the models. So keep an eye out for that. We also hope that you'll check out our latest manuscript in PLOS ONE. In this manuscript, you can learn in detail about each of these null models and the mathematics that goes in behind them. Data and code is available to replicate not only all the results you see in this talk, but every result in the paper. And you can find this paper at this link here. In addition, you can check out Zach's page on his website for all different things, backbones, talks, slides, etc. You can also head to Backbone on GitHub if you see anything that you think could be improved or you see some functionality you'd like to add. And if you have any questions or comments, you can always contact us on Twitter or shoot us an email. And thank you very much for listening. I hope you guys check out Backbone and that it can help in your research. Thank you.